Welcome back to Larry's Classroom. We have talked about series circuits, we've talked about parallel circuits. We're going to begin today talking about circuits that have both series components and parallel components to them. So we're going to start by drawing a circuit here. Power supply, 6 volts, negative and positive. We're going to draw a couple resistors in series. R1 equal to 1 k ohm. And we're going to have R2, which is also be 1 k ohm. R2 equal to 1 k ohm. And now we're going to have a couple parallel branches. R3, which will be 2 k ohm, and R4, which will also be 2 k ohm. Now we're going to think about how we analyze a circuit of this type. And the first thing we'd like to do is simplify this circuit a little bit. Let's draw another version of this circuit. We're going to combine this R1 and R2 in here. 6 volts. And we're going to call this RS, which is going to be equal to the sum of those two. We're going to call that 2 k ohm. 1 plus 1 is 2 k ohm. And we're going to still leave the parallel branch in here. Still going to have R3, which is equal to 2 k ohm. And still going to have R4, which is still going to be 2 k ohm. I'm going to call this circuit number A just to kind of keep track of the order we change them. 6 volts still here. We'll call this circuit number B. We're going to simplify the circuit just a little more by combining the two parallel resistors, R3 and R4. And these are both 2 k ohm. And you remember when we have N equal resistors, we have that R total, or R equivalent, let's call R equivalent this time. R equivalent equals 1 over N. Because they're equal, we have two of them. So we're going to say here that R equivalent, we'll calculate right here. R equivalent equals 1 over, this is R over N. R over N. R equals R over N. So we have 2K is R. And we have two of them. So R equivalent would be 1K ohm. So we're going to redraw the circuit with a single 1K ohm resistor in here. 2K. We're still going to have the 2K here, but the parallel network will be a 1K. We're going to call this RS equal to 2K. We add those together, 2K ohm. And our parallel, I'm going to call this, which was the parallel combination of these two, which we found to be 1K ohm. Now, I'm going to simplify it one more. Remember, we add these two series resistors. All we have is series resistors now. So we're going to add those to make a single resistor. I'm going to squeeze this in over here. It's a little, we're going to call this circuit C. And over here, we're going to put circuit B. Or circuit D, excuse me. And it was still a 6 volt supply. 6 volts minus plus, and now it consists of a single resistor, which we'll call the R equivalent that we did here. REQ, which equals the 1 plus 2 is 3 k ohms. So we simplified this circuit in 3 steps. We took the original circuit and we have a series section and a parallel section. And you might also notice that this series section is in series with this bank of resistors, but this here, we'll talk about it. So we simplified it first by adding R1 and R2 to get 2 k ohms. Now here, what we want to talk about is neither of these resistors are actually in series with R3 or R4. You remember that in a series network, the current is the same everywhere. Now R1 and R2 are going to have the same current. Whatever current we get is going to flow right through both of them. But what's going to happen at this point, the current's going to divide. Some of it's going to go through R3 and some of it's going to go through R4. So even though R1 and 2 are in series, neither of them are in series with R3 or series with R4, because you see that the currents are different. Same thing here, the R series, which is the sum of those two, is not in series with R3 for the same reason. Now we utilize the R equivalent for, I'm just going to say R here because I've used REQ over there and I don't want to use it twice. The formula, when we have multiple equal value resistors in series, we simply divide by the number of resistors. So we took the two k ohm resistors, or 2 of them, divided by 2 to get 1 k ohm for this little piece, which we called RP. Let's call it RP here. R parallel. Then we replaced this bank of parallel resistors with a single resistor. So now we have a series circuit with a 2 k ohm resistor in series with a 1 k ohm resistor, which is the equivalent of this parallel branch. This 2 k ohm is the equivalent of this series section. We combined them again to make our calculation a little bit simpler. So let's find out what the total current here is. And we're going to use this formula that we've used many times. I equals voltage divided by resistance. We've used this enough times, it's probably starting to get ingrained in your mind by now. So we have 6 volts, and we're going to call this I total, which is the total current from the power supply, is going to be the 6 volts of the power supply divided by the R equivalent of 3 k ohms. And you remember when we take voltage and we divide it by k ohms, we get an answer in milliamps. So 3 into 6 is 2, so we have here 2 milliamps of total current coming from the power supply. And let's put that on each of these drawings. 2 milliamps. Here we have the same 2 milliamps. And here in the mainline part, but not through these branches, we have 2 milliamps. And here 2 milliamps. Now, let's think about what the current will be through each of these R3 and R4. Well, being that these are both 2 k ohm resistors, the current will split equally. Whatever voltage appears across either of those resistors will be the same. They're the same resistance, so they're going to have the same amount of current. So we're going to have this 2 milliamps going to split. We're going to have one milliamp here, through, I'm going to put that down below, there's a little more room. 1. Through R3 we'll have 1 milliamp. And the same thing we'll have through R4, 1 milliamp. Put the 1 milliamp here. So we've took our original series and parallel combined circuit. We first combined the two series resistors, replaced them with a single 2 k ohm resistor. Power supply stayed the same, the parallel branches stayed the same. Then we took the two parallel branches, and being they were equal, we used this R over N formula, divided the 2 by N to get 1K. So replace this parallel network with or parallel bank of resistors, if you like to call it that, with a single we call it RP, equivalent resistance for the parallel network. Now to simplify a little bit more, we added the R series that we got from combining these of 2 k ohm and the R parallel that we got from combining these to get 3 k ohm. We reduced our original series and parallel circuit to a single resistor circuit. And from there it was quite easily to calculate the total current, which being this series circuit, total current is the same everywhere. That was still good all the way through this circuit. Again, you see we're going from negative, positive, which we call electron flow. So we're doing this in terms of electron flow rather than what we sometimes talk about called conventional current flow. Anyway, but here we didn't have a series circuit all the way. They had to divide, and we saw that they were equal resistances, and what's going to happen with equal resistances, the currents will divide equally, and that's because the voltage across both resistors is the same, and because of Ohm's law, you cannot have two different, the same voltage and the same resistance in two different current values. So there's our introduction to series and parallel circuits. We utilize, in this case, for the parallel combination, we use this R equal to R. I'm going to call this RT. Let's call it RP, R parallel is equal to R divided by N. R of each branch, so they have to all be equal to use this formula. And we used our Ohm's law, I current is equal to voltage divided by resistance to solve for current. And we worked our way back, we looked at how to divide it, and here we have our original series and parallel circuit with all the currents in each position. And just for kicks, let's quickly do the voltages across each of these. So R1, we have, remember, voltage equals I times R. And when I is in milliamps and R is in k ohms, voltage is in volts. So 1 times 2, we have 2 volts. 2 volts there. Again, 1 times 2, we have 2 volts here. Here we have 2 milliamps times 2 k ohms. So we have 4 volts. No, this is 1 milliamp. Excuse me. After I split them, that become 1 milliamp there. I got a wrong value written there. So this is actually, this is also 2 volts. And the same thing over here, 2 volts. So our total is going to be the 2 volts here plus the 2 volts here plus the 2 volts here, 6 volts. RT equals, we'll call these voltage 1 plus voltage 2 plus voltage 3 equals 2 plus 2 plus 2 equals 6 volts. Same as our supply. So we've analyzed all the currents in this series parallel combination. it's a natural progression from the things we've been doing with just series and just parallel. You're going to see both in one device, so add a little bit more to your network analysis skills here. Now we'll move on a little bit. We're going to talk about resistance strings in parallel. We're going to think of what we had. We have four 60 watt 100 volt 120 volt light bulbs. I'm just called lamps. We want to run these off a 240 volt supply. Let's think about what we could do. If we start with 240 volt supply and we put a single light bulb, a single lamp across that 240 volt supply, well, this lamp is rated for 120 volts. We're going to have excess current. The power consumption will be high because the voltage is doubled, and actually the current will be doubled. We will have actually be putting 240 watts on that 60 watt light bulb, which is going to overheat it. It's not going to last very long. So I'm going to write too bright here. Too bright. Now we're going to try another situation. We're going to put all four of the lamps in series. So if we put all four lamps in series, we'll draw four lamps. And again, we're going to run on the 240 volt supply. But being these are the same wattage and same voltage, the resistance of each lamp filament will be equal, which means the voltage will divide equally amongst them. So we're going to have 60 volts on this one, 240 divided by 4, 60 volts on this guy here, 60 volts here, and 60 volts here. So what we see is we have 120 volt lamps with 60 volts on each one instead of 120. That's a lesser voltage. It's going to reduce the power output, and half voltage will half the current. Half current times half voltage will be 1/4 wattage. So we'll end up with really only 15 watts on each one. That's going to be basically too dim. So let's try one more way of wiring these four lamps in attempts to run them off of a single 240 volt power supply. This time we're going to make two parallel branches with two lamps in series in each one. Now what do we have here? We have the 460 watt lamps, 120 volt, still equal resistance. So they're going to divide the voltage equally. So we'll end up with 120 volts across this lamp, and 120 volts across this lamp, and 120 volts across this lamp, and across this lamp. Now, as you recall from initially, these lamps are 120 volt lamps. So by connecting these lamps in this configuration, we have found a way to supply all four of these 120 volt lamps from a 240 volt supply and have the correct voltage on each one, so the lamps will operate as they should be and everything is just right. Now, one thing you might notice about this last circuit that we put together, if we look at this half of the circuit, it's totally independent like all the other parallel circuits we've seen, and the same with this one. We have 120 volts, 120 volts. Everybody's happy. Our lamps are putting out their proper wattage, proper brightness. Nobody has excess voltage or too little voltage, and they're running very fine. Our four 60 watt 120 volt lamps are running off a 240 volt supply. They're each producing the 60 watts they're supposed to. We're getting a total of 240 watts from those lamps, and it's working just perfectly. It's just right. We'll move on a little more. We'll talk about another circuit of a series and parallel variety. This circuit is resistors rather than lamps. We have two resistors in series, which we'll call R1, 6 ohms, 6 ohms, and R2, which is 4 ohms. Then we're going to run this on a 10 volt supply, 10 volts, minus plus. Now we have another parallel branch. This is R3, we'll call that, and it's 5 ohms. Let's start by figuring out what the current in each branch is. We could redraw this. Let's do that real quickly. Now listen, we could redraw this, but it's pretty easy to see that 6 ohms and 4 ohms is equivalent to 10 ohms. So we'll call this branch 1. So we'll find I1, which is in that direction. This is going to be I2 and I3. We'll call this branch 1, this branch 2. So the current through branch 1, we're going to use we've used this many times, current equals voltage divided by resistance. We have 10 volts applied to both branches. We have a total of 6 ohms in branch front 1, so we'll say that I1 is equal to the 10 volts applied to branch 1 divided by the 10 ohms. Total resistance of branch 1, 10 divided by 10, we got 1 amp. This is volts divided by ohms, so it's amps. So we'll put that right here. We'll say, we'll write 1 amp right here. Now let's take a look at, we'll call this I2 through branch 2. I2 is going to be the same 10 volts supplied, and we're using this formula right here, volts over resistance. Some may say volts over ohm. We have 5 ohms. And what do we get there? 10 divided by 5, we have 2 amps. So this guy here is 2 amps. So we have branch 1, current 1 amp, which was our 10 volts divided by 10 ohms. Branch 2, current 2 amps, which is our 10 volts divided by our 5 ohms. And let's see what our voltage drops are going to be across all of these resistors. Well, we're going to use this formula, voltage equals I times R. We have resistance in ohms, current in amps, so we're going to get result voltage in volts. So let's look at R1. We'll call this voltage 1. Voltage 1 is going to equal the current through resistor 1 times the resistance resistor 1. Well, we calculated branch 1 amp. So we have 1 amp. And we're going to multiply that. I'm going to put the dot symbol this time. Times the resistance of R1, which was 6 ohms. And that gives us 6 volts. And let's see what the voltage across R2. V2 going to be the same formula, current times resistance. Same current, 1 amp. And we're going to multiply that times the resistance of R2, which is 4 ohms, a different resistance than the first one, is 4 volts. So I'm going to write right here 6 volts and write right here 4 volts. Now let's add those together. Remember our voltage total in the series circuit. It was VT equals R1 plus R2 on out to however many you have. We have 2, R1 and R2, so our VT is equal to the V1, which is 6 volts, plus V2, which we found to be 4 volts, which equals 10 volts. And you'll see it, as we've been saying all along, needs to be for consistency, that 10 volts is the same as the applied voltage. The voltage sources add up to the same amount as the voltage consumers or voltage drops. We don't need to do this calculation for R3 because these two parallel branches, the applied voltage appears here, same voltage on the both of them. Now let's figure out what I3 is. And we're going to use our I total formula. We'll write that over here. And this is for, remember, I total for parallel branches. We take the main line current, or I total, is equal to the sum of the branch currents. So we'll go I1 plus I2 on up to however many branches you might have. In this case, we only have 2. So we're going to say that our I total is equal to branch 1 current, 1 amp, plus branch 2 current, which we found to be 2 amps, equals 3 amps. So that 3 amps for total current, we're going to write that right up here. I'm going to erase this and put it in red. I total equals 3 amps. And you know, this is consistent with the things we've been saying. The main line current is the sum of the branch currents. Here the main line current 3 amps splits with the larger amount going through the lesser resistor and the smaller amount going through the larger resistor. And we end up with 2 amps through the smaller resistor and 1 amp through the larger resistor. We had equivalent resistance of 10 ohms. So 3 amps splits into a 1 and a 2, and actually it comes back here, it recombines, and we get 3 amps here too. You see the current comes from the electron flow from the supply, splits 1 amp down branch 1, 2 amp down branch 2, comes back together, adds back together. Now let's think about what our total resistance is. We can do total resistance. I think we've had before that our total is going to be V total divided by I total. And this comes right from the other form of Ohm's law, resistance equal voltage divided by current. I for intensity in the case of current. So we calculate our T, which we Now we've calculated VT, or given VT, 10 volts. So we're going to write there, we're going to say RT, the resistance of the total resistance of whatever we see over here, is equal to the voltage applied, voltage total 10 volts, divided by the total current, which was 3 ohms, or 3 amps. And this becomes 3.33 ohms. This would be a continuously repeating 3, but I'm just truncating it to 2 decimal places here. And you might remember we said that in a parallel branch, the equivalent resistance, or the RT, is less than the smallest branch. Well, our smallest branch was 5. 3.33 is less than 5. Our largest branch was 10. 3.33 is also less than 10, but it's always going to be less than whatever the lowest resistance in there is. Now let's think about another way of calculating this. We can redraw this piece, 10 volts. And we're going to look at this and replace it with a single resistor. 6 and the 4 gave us the 10 ohms. And this we leave alone, 5 ohms. And you remember our parallel resistance formula for 2 resistors? We had that R, I'm going to call it EQ this time, is equal to R1 times R2 over R1 plus R2. R1, R2, we're going to call that, reuse some numbers for the sake of this particular formula. Well, so we take this same formula, REQ is equal to R1 times R2, 5 ohms times 10 ohms, 5 times 10, that's your numerator of your fraction here, and the denominator is R1 plus R2, so it's 5 plus 2. Let's change the order so they match the way they're written, not that it matters. Addition and multiplication are both commutative, so order don't matter, but let's put them in the order I've drawn them. 10 times 5 and 10 plus 5. So we end up with 10 times 5 is 50, and 10 plus 5 is 15, which also works out to 3.33 ohms. And that's good news. We don't like to do problem 2 different ways and get 2 different answers. Another thing you got to remember when you're applying Ohm's law to these series and parallel combination circuits, and this one had series here and parallel there, the current in the series parts of the circuit is the same everywhere. In other words, we had the same current through R1 as through R2. And the voltage across parallel combinations is the same in all branches of that parallel combination. So the 10 volts applied across branch 1 was the same as the 10 volts applied across branch 2. And if you're trying to find out your total resistance using this formula, we have to have all of the R in the entire resistance, the entire network has to be in this particular R when you use that to find out the total current of the supply. And of course, let's just do that real quick. We'll say IT, and we'll use this voltage of the supply. I'm just going to say voltage applied equals RT, which we calculated to be 3.333. So that's 10 volts divided by 3.33 ohms, and 10 divided by 3.33 is 3 amps. So we kind of went full circle here, and everything is in agreement. But when you want to find IT, looking at the supply, you got to have all of the resistance out here. If I had another resistor here and I forgot to account for it, this would not give me a correct answer. But we, in this case, have utilize the entire amount of resistance, which we found two ways. One by solving for the current and using the voltage. The other by doing the series resistance to 10 and then the parallel resistor formula for two parallel resistors. Always make sure you include all resistance if you want to find out the current being supplied by the source. If you miss one, you're going to get an error in your calculations. We're going to talk a little bit about resistance banks in series. So we're going to draw another circuit here, and we're going to look at what happens with that circuit. This is going to be a different kind of a series parallel circuit. We had two series in a parallel. We had two series in a branch and another parallel branch. Oh, I'll draw it. We had one that looked like this. We had one that looked like this. And we're going to have one more. It's going to look a little bit different. We're going to apply 48 volts to this thing. And we're going to have parallel branches up here. And in series with that parallel bank of resistors, we're going to have another resistor. So you see, we have a series parallel circuit. I'm going to use this green pen, and I'm going to circle all the series parts. There's your series part. There's your series part. I'm not going to do it over here because I'm still working with that drawing. I'm going to use the red pen, and I'm going to circle the parallel part on these two. There's the parallel part, and this one, the whole circuit, is the parallel part. Series, parallel, series, parallel. Here we got parallel series. So put some values on this thing. I'm gonna call this R1, 20 ohms. R2 also gonna be 20 ohms. R3, which is going to be 2 ohms. So the first thing we probably want to figure out from this thing is what the total current is. So how would we do that? Let's think about that. Total current, again, we're current equals voltage divided by resistance. We have a voltage, we need to find out a total resistance. So let's what we got? We got 220 ohms in parallel, so that's just going to be 20 divided by 2, the old resistance of the parallel branches when they're equal is the resistance of one branch divided by the number of branches. So we're going to solve this by saying that our parallel equals 20 divided by 2 equals 10 ohms. So we're going to redraw this same circuit, but now we're going to have a 10 ohm resistor. 10 ohm, and another still got the 2 ohm. We still got the 48 volts. We can simplify this one more step. We can combine these two. These are resistances in series, so just add. So 48 volts, and those two combined become simply a 12 ohm resistor. So if we want to find IT, the total current from the 48 volt supply, we can utilize this formula, I equals V over R. We're going to call it IT, is the voltage applied, 48 volts, divided by the total resistance or equivalent resistance of 12 ohms. So what we now have is 4 amps. So we got 4 amps in this circuit. I'm going to put some polarities on them so my arrows match. 4 amps. 4 amps. So we simplified our circuit by we're substituting the parallel branches, combining the series branches to get the total. Well, let's think about voltage drops here. Let's see what the voltage across R3 is. Well, remember, voltage equals current times resistance. So we're gonna call the voltage across R3 V3. The 4 amps, using this formula, 4 amps times the 2 ohms. That's 8 volts. So we can put 8 volts here, because that's the 2 ohm resistor, 8 volts here. Now if we want to know the voltage across here, we could use the voltage total. Remember, voltage total in a series circuit, because this is now a series circuit. If we reduce those, voltage total would be V1 plus V2 plus on up to, we only have 2, so we can say the voltage total equals V1 plus V2. So the voltage total is given 48 volts. V1 we do not know yet, but we do know V2, so we leave V1 as a variable plus the 8 volts. So we calculate what's V3. It's V3, but it's just, we'll call it V3. V3, and we'll change our subscript here because those are the 2 we had. V1 plus 8 volts. And if we solve this, it ends up being V1 equals 40 volts. We simply subtract the 8 volts from both sides. So we got 40 volts here across this 10 ohm resistor, which also appears across this network here. And I'm going to put a couple of points to indicate the ends of where that 40 volt appears. So we utilized our voltage sum around a series circuit to come up with the voltage across this piece. Now, we want to know the current through R1 and R2. We know our total current is 4 amps. We can do this 2 ways. Because these are equal resistors, the current's going to split equally. So the 4 amps that we have in the whole circuit will be equal to, we'll call this I1 through R1 plus I2 through R2. But because they're equal resistance, they're going to be equal. So 4 divided by 2 is basically going to be 2 amps. And the 4 amps will equal 2 amps plus 2 amps. Now the other way we can solve those currents through these 2 parallel branches is we could have calculated the voltage here, which I believe we've already done. Yeah, we have 40 volts here. We'd used our voltage total formula for a series circuit to get the 40 volts here, which also goes up there. And remember, voltage, let's see, current equals voltage over resistance. Well, for each of these R1 and R2, if we want the current, that's going to be the voltage, 40 volts, divided by the current, divided by the resistance, which was 20 ohms, which is also 40 divided by 20, 2 amps. So there's no need to do the other one because it's the exact same resistance. And we know in parallel branches the voltages have to be the same voltage, the same resistance, you're going to get the same current. So we have consistency here. Our 4 amps here splits into 2 amps, 2 amps. It recombines, now it's 4 amps, through the R3 and on back to the supply. And I'm going to circle, now that I'm done scribbling in this drawing, I'm going to put a red circle around my, what I'm calling the parallel portion. And I'm going to put the green circle around the series portion. So we've got 3 different series parallel circuits that we worked with. We had this one with a series combination, which in a parallel section. This one with a series section, the whole thing was a parallel section. This one we got a parallel section, and the entire thing is a series section. So we've made several different ways to look at series parallel, series parallel, series parallel. The same techniques of analysis apply. You want to simplify where you can. We simplified by combining this, and then we simplified by combining the series. That allowed us to find the total resistance. And again, we made sure we used all of the R when we calculated the current from the supply. Always make sure when you're solving a network like this that you don't miss some piece out there. We had this bank of parallel resistors. We made it into a single 10 ohm resistor. We combined the 10 and the 2 into 12, divided by 48 by 12, got the 4 amps. Then we worked our way back using voltage drops, or we often call IR drops. And then we used a current divider formula here because they were equal. And we also solved the same branch circuit current, the branch currents, by using this formula and the voltage we found when we calculated voltage drops and the given resistances. Anyway, I think we'll call that good for today. I appreciate you coming back. Be sure to like and subscribe. And until the next time, keep on learning.